Hello, this is Mark Unkefer, Director of the Fiber Optic Sensing Association, and welcome to this month's webinar, our part of our monthly series of webinars in which we feature different aspects of fiber optic sensing technology. This month, we're able to present more information about high fidelity sensing, focusing on the experience of Hifi Engineering, which is one of our member companies. Our presenter is Steve Koles, who is the President and CEO of the company. He's also been in the industry at Steeper Energy, President and CEO of Hemisphere GPS, and a Vice President and GM at AOL Time Warner in Canada. Steve's a graduate of the University of Alberta and also the Executive Management Program at the University of Western Ontario's School of Business. Steve, we're really interested in learning a lot more about this particular approach to how to use fiber effectively to do sensing. Thank you.
Well, thank you very much, Mark. We very much appreciate the introduction. We're honored to be a new member of the Fiber Optic Sensing Association, and very excited about being here today to talk to everybody about using high-fidelity fiber optic sensing for world-class pipeline monitoring. What we hope to accomplish today is talk through a little bit. We'll obviously give you a little bit of background on who is Hifi, and then we'll talk a little bit about, or a lot about, world-class pipeline monitoring, including what exactly that is and how we believe we can actually achieve that. As part of our message, we really want to provide a bit of a background here. As many in the industry will know, there's been quite a bit of testing around fiber optic sensing for pipeline applications. We're very proud to say that the technology is definitely proven, viable, and frankly now very commercially available for world-class pipeline applications. A little bit about Hifi Engineering. In our background, we've actually been around for about 10 years here in Calgary, Alberta, Canada. We are a technology company with fiber optic sensing technology. We started in DAS and DTS many, many years ago, but have since worked to develop a more turnkey called distributed fiber optic sensing system and interpretation software that is higher quality from a performance perspective and a data perspective. You can actually see we have some strategic investors in our company, both Synovus Energy and Enbridge. As a result of that, our exclusive focus is really downhole and even more so now pipeline safety and pipeline monitoring. We've used the technology for many years and now closer probably to 2,000 wellbores on a downhole basis, but been very, very focused on pipeline monitoring. And along the way, we've created a partnership with Baker Hughes, a GE company, where we're using their GE Predict software as part of our turnkey answer product, as part of getting information from our fiber optic sensing in the field into the control room. The challenge that we've gone out to try to solve in the industry is really simplistically around a challenge of space and time. Whenever there's an issue, whether it's a leak incident or other type of incident that occurs within the pipeline industry, typically the breakdown or challenge that operators have is determining exactly where and when that event has actually occurred. Today we use point sensors like flow meters as an example and run protocols like a mass balance system between those. But the challenge is they may be separated by significant distances, or not have the resolution or accuracy to be able to find small events like a pinhole leak. We can also do things like periodic surveys, whether it be manually, through inline inspection tools, smart balls, drones, even dog sniffers. But if they're not at the right place at the right time, we always then have the challenge of space and time. But from a sensing perspective, we can actually define world-class pipeline monitoring, meaning the ability to detect leaks or other preventative types of events with 100% accuracy and without false positives along every centimeter of the pipeline asset and in real time. By the way, I'm going to make an apology in advance. I am sitting in Canada and I am going to speak metric, so apologies to all of our American friends. So So the question and the challenge that we have is, how do we achieve this type of vision from a pipeline monitoring perspective through complementary systems, through a new technology? And of course, without the drum roll, we believe that doing so using high fidelity fiber optics as an intelligent sensor is a way and a process to be able to solve space and time. Now, I'm going to pause here for a moment, and I do want to be very respectful to all the different types of fiber optic technologies that exist, either among the different FOSA members as well as just in the general market. We believe there is not a single fiber optic solution that can address all applications for all industries. It's the same analogy as that we all drive different types of vehicles depending on our chosen application of getting from A to B. What we provide, and others provide, very specialized fiber optic technology in various industries as well. We have a very specialized and very targeted application to pipeline applications only. We also don't market this outside of the oil and gas sector because we just simply don't believe that one size fits all. Now, our fiber optic technology, as you'll see as we get into a little bit more of the details on it, is, number one, fully distributed. It does sense every centimeter of the asset in a dynamic range. It does so with very high fidelity in terms of resolution of integrated variables such as acoustics, so sound, thermal energy, so delta temperature changes to resolution of 0.001 degrees Celsius, as well as very high accuracy, vibration, and strain. And with that, we can actually provide a solution to space and time by providing 100% coverage of the asset on a fully distributed basis and sensing with the speed of light 24/7 in high performance or high fidelity. Now, I say high fidelity a lot. Obviously, it's a big part of our name. We do not have anything to do with 1980 stereos, but we are about high fidelity sensing. And there's an analogy we like to bring forward here in terms of a human analogy. We rely on high fidelity sensing through all of our senses to make intelligent decisions every single day. I've mentioned I live in Canada. In the wintertime in Canada here, it gets very cold. If you wear glasses, like I do sometimes, and you're outside in the cold, what will happen is your glasses will fog up. What happens is you're losing or impairing the fidelity factor of your sensing, your vision. And when that occurs, you now start making less than intelligent decisions in terms of with low fidelity vision, you're going to bump into walls or posts and things like that. What we're here to say is actually high fidelity sensing for pipeline assets is exactly the same thing. We rely on high fidelity to make intelligent decisions. And we've tried to apply this through the same in terms of world-class sensing through the Hifi's platform. We call it high fidelity dynamic sensing, or HDS. And so it is a little bit unique in the industry in terms of other fiber optic sensing technologies. Number one, it is engineered from the ground up to be designed for sensing and doesn't use a telecom fiber infrastructure to be able to do that. It is also integrated from the perspectives, as I mentioned, of acoustics, temperature, and strain, all in one system, and frankly, with one sensing fiber. And then because of our optical architecture, we've also been able to optimize this to operate very well from a sensing perspective over long distances. And as a result, that makes it very applicable and more suited for pipeline type applications versus other shorter type of applications. And so with this higher fidelity, we believe we can actually do things like provide 100% alarm accuracy without false positives and be able to provide intelligent decision-making back to pipeline operators through the whole application of preventative pipeline leak detection. Now, how we do it, we're not going to go into too much technical detail here today. As I'd mentioned, there's lots of different types of fiber optic technologies or approaches to interferometry, such as backscatter. If you're interested in that details, there's lots of information on the FOSA website. The key challenge really, as we found in pipeline monitoring on a world-class basis, is having very high signal-to-noise ratio, or maximizing the fidelity. And while we use a number of techniques around the design of our specialized sensing fiber, one of the areas that we do use is a fiber Bragg grating, or FBG. Now, the definition of an FBG, you can look it up on Wikipedia, talks about a segment of optical fiber that has an etching in it that will then reflect particular wavelengths of light, transmit others. We can therefore use this as an inline optical filter to either pass through certain wavelengths or block other ones. And that actually allows us to use it as a wavelength-specific reflector in a way. Now, typically in lots of fiber optic sensing, FPGs are used in other specialized cable to measure spectral shift, specifically around for things like strain and temperature. We actually don't use FPGs that way. Hifi uses FPGs as a reflector to create essentially an interferometric cavity that we then can monitor on a fully distributed basis. So the result is we are not a quasi-distributed or point sensor-based solution. We are indeed using the technology on a fully distributed basis, and that actually provides an optical architecture for us that has linear consistency over long distances. What I mean by that is having good data quality at the beginning as well as end of, in this case, the pipeline asset. In terms of other areas of how we do it, having a high fidelity sensor providing great data is a good place to start. From there, we run a variety of different algorithms, machine learning algorithms more specifically, to be able to discern different anomalies from others, like differentiating temperature from strain is a really good example of that. We use a variety of software analytics there to find what is abnormal from differentiated from normal operations to the pipeline, and be able to provide that information then very quickly back to the control room of that pipeline operator. And as I'd mentioned, Hifi has partnered with Baker Hughes GE to use their Predix platform as our real-time interface for getting this information back to the control room of pipeline operators so that they then can make intelligent decisions in real time. So we're really coupling a very high fidelity sensor technology with our own software algorithms, as well as then the Baker Hughes Predix platform for an answer product that becomes much more turnkey. Now, I mentioned in the outset, pipeline testing has been significant around using fiber optic technologies. We've been involved in that, as many of the FOSA members have as well. We've been able to find that providing multiple variable analysis, again, sensing acoustics, temperature, and strain are very, very key for world-class pipeline monitoring, and we've been proving that through quite a bit of large-scale testing. Relying on one variable may drive potential false positive alarms, and that's a significant issue in the pipeline industry. You can actually see the illustration off to the right here where we're showing a illustration of a frequency of acoustics associated with a pipeline leak correlated directly with the strain on the pipe at the exact same time. We could extend this even further to provide also the thermal effect of a potential leak. In gas, you'll have a cooling effect, or what's known as the Joule-Thomson effect. Liquids or bitumen or others, you'll actually get a heating event that you can also then correlate. With that, that's how we've been able to provide very high success rate in terms of detecting leaks very accurately without false positives. You can actually see in the very right-hand portion of that illustration an example of a recorded sound of a leak where acoustically it's being picked up, but there is zero strain on the pipe. That would have generated a false positive versus a real leak alarm. Our scorecard through all the tests that we've been going through, whether that be in field environments, lab environments, has been very successful. We've detected multiple rate leaks very successfully without having false positives or even identifying false positive simulations very, very accurately. We've been tested in all kinds of different soil positions, different clock positions around the pipe, and through a variety of different types of products, whether it be gas, liquids, bitumen, multi-phase. We are really product agnostic, and we've proven that we actually can provide very good, accurate leak alerts down to very small leak orifices, as well as also at very small pressure profiles. Frankly, our results, we believe, speak for themselves. They've been tested very extensively, and while most of these test situations are, the disclosures are confidential, we do have some publicly available executive summaries available on request if you're so interested to learn more. So with that, we're going to do something a little bit different in this webinar. We have a little saying here at Hifi that talk is cheap. We'd much prefer to actually show you. So what we're actually going to do is actually move, and I'm going to turn on my webcam here. And what you should be able to see is an environment now where we've pulled up a camera and we're actually sitting in the Baker Hughes GE offices in downtown Calgary. And what we're actually going to show you here is an illustration of a little pipe setup that we have running live with our high fidelity dynamic sensing technology running. And what we're going to do is run a number of real-time scenarios, various preventative leak detection type events, and show you actually how they show up in our control room interface. Now, the control room interface is literally something that we've worked with Baker Hughes GE on developing. It sits within a standard Google browser in this case. It is a little boring in pipeline operation control rooms. Gray is good and color is bad. So when there's nothing going on, which is most of the time, frankly, the illustrations become fairly benign. But when we go through a variety of events here, you'll see how this works in real time. And I want to point out, this is not fake. This is happening in real time. It is a little gutsy, but we're going to give it a try. I'm going to introduce actually my assistant, Daniel, one of our system engineers. He's going to wave for the camera. He's going to walk in towards our pipeline here and start showing various events. We'll actually end with a leak simulation, but we're actually going to start with a thermal anomaly. So Daniel's actually going to walk over to the pipe, and he's going to turn on a couple of floodlights. These floodlights are going to start heating up the pipe and start creating what we'll call a thermal anomaly. It's not that it's an anomaly because the pipe is heating. Heating and cooling of a pipe happens naturally throughout the day, but the anomaly is something that's providing some degree of intensity as well as a location-specific portion of the anomaly. And so as he does that, I'm going to switch over back to my control room interface. You can see that literally in real time, we've created this temperature alarm. We have specific GPS coordinates of where the event has been detected. We've brought up this map where we can superimpose pumps and valves and a location of where the temperature anomaly has been occurred. We can actually zoom into that. It'll take us right downtown to Calgary where the Baker Hughes GE offices is in terms of where this location has been detected. We can actually zoom in terms of additional detail behind the event itself. In this case, we're looking at a thermal deviation of beyond what was normal or beyond what was essentially the baseline. We can look at this event as a schematic instead of a map if that's the preference of the operator, where we can show the kilometer or milepost marker situated around different assets that might be relevant. I can, from a process floor, acknowledge this. I could enter in comments around this being a test, or in this case, maybe it's a possible forest fire that might be occurring that's getting too close to our right-of-way, and we may want to consider a preventative shutdown of the pipeline. But otherwise, I can close the event down and actually log it as event, and now we're down to a situation where we have no new events that are outstanding or unacknowledged in the process flow of our pipeline. Now, the next event that we're actually going to show you is, I'm going to bring back up my camera, is going to be a security intrusion or third-party interference. And while this could be entirely an accidental event, like a construction machinery or excavator or hydrovac, we can also do things like intrusion detection for hot tapping, which is still alive and well in the industry. So I've actually now brought up back to our control room. We have this intrusion alarm. It looks very similar to the previous alarm. This one is a little bit different in that it is entirely an acoustic anomaly. And here's something that's actually fairly compelling in our answer product, is in seconds after this has been detected, we can actually play you the audio of what was picked up at the exact location of where it was picked up. So if I actually play this, you're hearing that off of my laptop, so I don't know if it's coming through very well. And you could actually still hear me speaking, and it shows you just the fidelity factor of the system and what it was actually able to pick up after the system picked up the intrusion alarm itself. Now, again, in the realm of preventative pipeline leak detection, areas that we get a lot of attention to are things like abnormal strain and vibration. This might be due to geotechnical activities, earthquakes, landslides, or otherwise creation of strain events that are abnormal. And you could see there that Daniel sat on the pipe, creating now an abnormal strain event. The human eye couldn't tell that our pipeline was straining, but the sensor was able to pick up. This one, again, from the perspective of you were seeing essentially a deviation entirely correlated to the weight of Daniel sitting on the pipe and creating this defect. So again, we can acknowledge this alarm and collapse it. Again, we're back to the zone of no new events. The last event that we're actually going to show you is an actual leak event or leak simulation. Of course, I'm sitting here on the 10th floor of Gulf Canada Square in Calgary, Alberta. Baker Hughes doesn't let me put product in that pipeline, let alone leak it around the floor. So to simulate an event, we actually have an air compressor tucked in behind our asset that is charged fairly low pressure, around 15 psi. We have a hose that's connected to the outside of the pipe. And we're going to open up the valve on that air compressor and simulate the effect of a leak alarm by blowing air on the outside of the pipe. And so you can now see, actually, now we've got our leak alarm. You'll notice this one actually looks just a little bit different from some of the other alerts. We've literally done focus groups with a number of pipeline operators who've said, if we have a real leak alarm, we need to treat it as such to follow our suspected leak procedure. I know many operations that have a 10-minute window to validate or invalidate such an alarm. In that case, we've been told we'd much prefer just to bring up the schematic to be able to show us what assets might be relevant, what pumps are in play, so that they, if they do need to do a shutdown, know exactly where they should be operating and what different assets they need to be managing and manipulating. So with this, I'm now going to move back over to my PowerPoint. I'm glad that actually worked fairly well. I again want to point out that was entirely live. I can stop sweating a little bit now, but we were happy to be able to showcase a little bit of just how the technology works in high fidelity and also in real time. A couple illustrations I wanted to continue on through the webinar with. That is specifically around fiber optic deployment. How do we actually deploy our fiber with pipeline? We actually have 3 deployment methods that we use. We call it very simply on the pipe, near the pipe, or internal to the pipe. We actually can use examples where on a greenfield or brownfield build, we are strapping electrical conduit to the pipe. We are a big partner of Durline, who is also a FOSA member. We prefer to put our specialized fiber in microduct-based conduit versus direct bury cable. We find this future-proofs the asset to provide future optionality of different sensor types potentially down the road. It's much, much easier for any sort of repairs that we hope never actually have to happen. It's very consistent with dig once legislation that's on the horizon for pipeline operators, and also gives great signal to noise ratio from the deployment of the conduit with the pipeline. Now, we don't actually have to be touching the pipe. We can actually just be near the pipe. It may be a case where the trench is not applicable or safe to have people involved or down to be able to strap conduit to the pipe. There also may be multiple pipes in the trench. In fact, I've got an example here to show where instead of actually placing the conduit on top of a specific pipe, we can actually be between different pipes. And that's a good example of near the pipe deployment. We've actually been very successful in detecting leaks very far away from the pipe. Of course, closer is always better as it relates to any sort of asset monitoring. But our spec is essentially 1 meter or less close to the pipeline asset for to be able to have effective leak detection. And while we can do that in new builds as well, we can also do micro trenching of the conduit close to existing assets, again, about 1 meter or less, that allow us to approach the retrofit market. And then finally, we also have internal deployment, which we have used for very short, high consequence areas. River crossings are the really good example of this. Typically, we'd place the fiber optic sensor in a stainless steel cap tube, and we would use an ingress point with a pack-off gland, an injector system, and a tow pig to be able to push and pull the line into place from the inside, and we can then actually monitor that pipeline from the inside rather than from the outside. Now, we have a retraction capability. If there was to be an inline inspection pig run plan, we can get the fiber out and then redeploy after the pigging is done. And we're doing a variety of tests right now actually to see how we can coexist with the fiber line staying in place with testing just with basic cleaning pigs. Back to an example of near the pipe deployment. We actually would deploy that again, that Durline conduit with our fiber optic sensor, either in at the time of burial or injected after the fact. Again, it gives that future optionality available to the pipeline operator. We would have breakout handhold junctions, usually around every 2,000 meter points, again, to be able to access the fiber either for installation or any sort of potential repair work that then terminates into a head-end type of architecture where we keep our light sources, our lasers, and our dense wave division multiplexing systems, as well as our interrogation units and CPUs for analyzing the data. Just another couple illustrations. You can see here placement of the orange conduit in the duct as part of the pipeline construction, and placement of the pipe itself, termination into, in the bottom part of the picture, handhold bolts, where we'll obviously coil up and pigtail a variety of different elements of the electrical conduit that we use from Duraline. We also have been have tremendous experience in horizontal directional drills, where we'll actually attach usually redundant conduit strings to the pole head, and we've done upwards of, I think our longest one was around 1,100 meters with Enbridge actually as a partner. That's an illustration down here on the lower right-hand corner. We've had to develop and worked on a variety of different elements of documentation and specification, particularly around construction and the placement of the conduit. There's all kinds of different methods around trench and trenchless based deployment methods that we can provide mainline contractors who may not have any experience with fiber optics, let alone placing conduit. And we have quite a bit of extensive library of documentation to be able to draw upon. But I'll just go through a couple examples of high fidelity sensing from the field rather than from an office space here with our test apparatus. This is an example of a roadway where we've actually have a buried pipe underneath this roadway about 3 meters. We actually be able to discern differences from a strain perspective from the compression of vehicle traffic along this road, whether that's a regular SUV or pickup truck versus this dump truck, that we've been able to discern differences in terms of it being empty versus it being full. What's interesting about this example is that we use this as a way to properly baseline the system, so that if we have normal vehicle traffic like this dump truck, we don't want to create a false alarm around that. So once we understand that this is normal activity around our pipeline, we would invoke it inside what we call our baseline, so that the system will ignore this type of activity but only focus on truer abnormalities or outside the thresholds set by, in this case, an abnormal strain. I showed you the example of theft detection from a hot tapping perspective. We've had lots of examples of excavators and hydrovacs that are out there in the field, maybe digging at the wrong time or the wrong place, and we've been able to successfully provide alarms back to our pipeline operator partners, so that they can properly remediate those threats, whether they be accidental or otherwise. Very good at detecting geotechnical activity. Earthquakes. Whenever there's an earthquake, we have a great ability to plot that energy wave across every deployment that we have, say, in North America. The most recent one was the earthquake from the Gulf of Alaska a couple of months ago. But this is an example here where we had earthquake at 5.2 on the Richter scale emanating from Helena, Montana, and we were able to pick it up 300 kilometers away at a deployment we have in southern Alberta, where it had dissipated to, on the Richter scale, about a 3.0. But you'll actually see here we were able to pick it up both acoustically as well as from a ground movement perspective, both the earthquake event itself as well as an aftershock that occurred about 5 minutes later. This type of information, as an anomaly, then can get alarmed back to the control room of the operator, so that they can make an intelligent decision on whether they should be considering some sort of preventative shutdown. It's not always about bad news events like geotechnical activities and earthquakes or third-party intrusion or leaks. We have the ability to be able to do things like pig detection and pig tracking through the digital signature that a pig will give off. Here's an example of a vibration pattern that happens literally every 53 seconds from this cleaning pig as it scraped through the weld joints, moving at a quarter meter a second. Once we actually were able to determine that that was what we were sensing, we realized that we were picking up this pig from 15 kilometers away from where the fiber was actually deployed, as that vibration will propagate up the pipe. So think about the ability to be able to do that same control room interface, provide an event detection that says pig detected, and also provide some sort of a dynamic icon going across mile post, kilometer post markers to be able to show exactly where that pig is moving to, and if it potentially gets stuck in any given location like a valve. And then finally, we also have the ability to monitor potential flow. whether that be simple batch changes and custody transfer, start-stop, different density changes, but even over time, the ability to look at flow deviations to what is normal. That might be due to corrosion or pitting or simple paraffin buildup. We could envision a day where we can use the same technology to tell operators when and where to pig. And by the way, it also does leak detection at the same time. And so we have a number of examples of commercial applications that we're working on that we'll be looking at rolling out very soon. We've been very fortunate to have a variety of very great partners to work with. We have over 350,000 meters of commercially deployed systems today, largely in North America. And you can see from some of the players that we've been working with, they range from mainline transmission companies and a variety of different midstream companies as well. And we've been very honored to be able to get some great references and acknowledges of our performance from some of these same players. Well, that actually concludes our webinar. We'd like to end by just saying by complementing existing or conventional, largely internal-based leak detection systems, we do believe by using high-fidelity dynamic sensing that world-class pipeline monitoring is indeed achievable and commercially available today. You can see we've got some videos that are actually posted on our website, and happy to answer any questions if you're interested to contact us. We provided our email address there on the last page. So thank you very much. I do appreciate everyone's time. Be happy to turn back over to Mark and to moderate any questions that might exist.
Thank you very much. And actually, let me just refresh for folks how to do questions. We have a text box over on the right where you can type in your question, and we'll be able to pass that on to Steve. We have a couple already. One person wanted to go back. You referenced a particular installation that you've done with Enbridge, and the question was, how long was that? I think that went pretty quickly, and they're kind of looking also, I think, to get some color as to what the capacity of fiber optic sensing is over distances. So could you elaborate on that?
Yeah, great question. So yes, that is a publicly disclosed project. It's Enbridge with the project was called Norlight, just north of Edmonton in Alberta. It's just under 40 kilometers, the entire deployment. The reference I made to them during the presentation was a very long horizontal directional drill under a river crossing that was around 1,100 meters and was pulled very, very successfully. Now, expanding on the question just around sort of distance, that is around a 40-kilometer system. Interestingly, we pull about a terabyte of raw data a day from that deployment. And so, of course, we can't transmit that type of data back to the control room. And so that's where using our algorithms, using edge analytics, and the ability to break that information down into event data and get it to the control room of the operator is very, very important. Now, back to the whole question of distance. We do have an optimized optical architecture that can allow us to do all kinds of creative things to extend distance at the requirement of the operator. We've looked at systems that could be, in excess of 100 kilometers. The reality is what we found is more important is solving for power, meaning that we do have to have equipment, having commercial grade power, UPS backup, a nice secure internal environment that's HVAC controlled. And typically that's going to be at some sort of, say, pump location. Where there's all kinds of commercial grade power already engineered. And so those are going to be, in a case of a new build, typically every 50 kilometers. We find ourselves in a position where we much prefer just to be in those types of locations and do a more decentralized type of architecture. It's a great question. Thanks very much.
Actually, we had another one that I think you just answered, but there was a subset question that this is having to do with spacing. Could you elaborate on how you get GPS coordinates?
Yeah, well, we will geocode the entire deployment. We do channelize our fiber with different wavelengths. That's part of how we use our optical architecture. We use a combination of dense wave division multiplexing and time division multiplexing. And so we will geocode the deployment even through physical structures like those handhold vaults, and we'll know which channels are where so that we then have the spatial resolution that we can be able to provide around any sort of event anomaly detected through that geocoding, and that's how we then upload it into, say, that Google map that you saw within the GE Predix interface.
Great. Quick question about, we've talked another distance, but this one is about the sort of shorter distance. You've mentioned that you look for a sort of optimal implementation, 1 meter or less. Is there a sort of maximum distance that you can? I realize the larger distance you go, you probably lose some of the capacity of what you can detect. But for, say, leak detection, how far away can you be from the pipeline?
Well, so you're absolutely right in that our specification is 1 meter or less in terms of having the sensor that close to the asset. With anything in terms of asset monitoring, the closer you are to the asset, the better. So even if we're not strapped to the pipe, if we can be tucked right beside the pipe, that's better than being a meter away. I can say that we actually have been tested in kind of real field environments where in some cases we were 3 meters away from the pipe and we were still able to detect simulated leaks both from the acoustic and strain signatures that emanate from the pipe when that occurs, as that energy will actually transmit through the soil as a natural conduit. Now you're absolutely correct in terms of the further we are away from the pipe, temperature or thermal deviation is much more difficult to be able to discern and detect. And that's, again, why the closer to the asset itself in terms of the pipeline, the better.
Next question is, can you expand on the interface with the GE, I guess it's Predix? Am I pronouncing that right?
You are indeed, yes. So as I mentioned, we use an edge analytic kind of platform in terms of running our algorithms on the data set that are coming from the sensor. And so that happens on a local basis right beside where we would have, say, our interrogators and light sources. What we then do is we run, essentially it's an edge agent software between our system and the GE Predix cloud. It is a cloud-based model and allows us to then broadcast on a one-to-many basis that information through the GE Predix cloud. And so that an interface can be the exact same interface in the control room, sitting on a much larger television screen, taking up real estate in the control room, or it can be the exact same interface then that a leak detection analyst might use at their computer, either at their office, or if they're working remotely because they've been called in or paged at an unruly hour, or even be able to access it on a mobile device. And so that's how that interface works. We'll send the event data from our system into the Predix edge interface software and then into the Predix cloud, which is their industrial internet software application that they use for all kinds of other applications that are, industrial or even military grade, such as asset performance monitoring.
So, Steve, the next question is: do you use special fiber optic cable, or do you use standard cable, fiber optic cable?
So our fiber optics are specialized. It is a specialized and proprietary design. I mentioned we do use fiber brag gratings or FBGs, but as a reflector, not as a point sensor. We do a number of other physical things to our specialized fiber itself to make it a high fidelity sensor. The underlying core is still single mode fiber, but as I mentioned, we do a number of physical things to the system design to make it a high fidelity sensor.
Now, we generally avoid cost questions, but I think we can maybe slip one in with this. Can you do a cost comparison with the fiber that you use, the specialized fiber you use with fiber generally? Is it how much more?
Well, sure. I mean, our fiber optics are specialized, and therefore they are more expensive than single mode fiber or multi-mode fiber that gets produced, in the hundreds of thousands of kilometers by manufacturing parties. Now, the good news is we've seen a tremendous amount of decrease in the cost of our fiber as we've been able to generate more manufacturing. So we do use now a couple of different manufacturers to be able to get lead times down from the perspective of getting fiber to market. And so while we are, now maybe 1 or 2 times more expensive than telecom fiber, depending on your strand count and how you actually create that definition. But it's significantly lower than even where it was 18, 24 months ago. And as we continue to do longer deployment, we're driving that cost down very, very low. And we do see at some point we'll be very cost comparative in terms of parity with telecom fiber.
Next question is, can you record acoustical data over the full length of the pipeline?
The answer is yes, and that's the beautiful thing of a fully distributed system, is that it is constantly recording in the case of the acoustics. And so when an anomaly is detected, we are able to record and play back effectively at a WAV file, the acoustic information, the acoustic data that was recorded at that location of the anomaly. You saw the example there where Daniel hot tapped the pipeline. Now easy because it's a 10-foot pipeline, but the more relevant examples we've had with excavators that are digging at at the wrong location or at the wrong time. The ability not just to be able to pick up the excavator. We've been able to pick up the idle of the excavator, and then as it revs the engine up about to dig, we've heard spotters talking or really yelling at the operator of the excavator prior to an event where they came very, very close to actually hitting the pipeline, to the point where we can actually make out voices and words. It is operating as a fully distributed fiber optic based microphone.
Let me see. The next question is a question about geo. You mentioned on downhole using some VPS imaging. What kind of geophysical imaging do you use?
I'm not entirely sure I fully understand the question. I mean, we do have a downhole business where we do deploy our fiber technology either on a downhole tool or actually on a distributed basis, say within a wireline or E-line, slick line type of deployment, even through coil tubing. Typically, our downhole business has been very focused on very acute anomalies. As an example, finding a pinhole leak behind layers of casing. In Western Canada, we're very big, largely involved in abandonments, where you're looking to diagnose the wellbore and understand where all potential problem points are that need to be remediated prior to the abandonment. If you're just seeking the loudest potential event in the wellbore and you remediate that, you may actually miss other locations within the wellbore that now become much more prevalent now that you've actually been able to remediate the loudest one prior to that. So that's where our applications on the downhole have been. We haven't done much in the way of other sort of louder events, frac monitoring or seismic. It's been very specialized.
And how far can you monitor with one interrogator?
Again, to us, the answer to that question is really more about power than actual sort of optical configurations. We can do all kinds of creative things with optics and light, duty cycling, optical switching to be able to leverage the power of an interrogator at a given location. As I'd mentioned, we've done configuration work around even 100 kilometers. But again, typically, I'm solving for power. And so we found that the most optimal location is to put those in locations where there's commercial grade power. Typically, that's going to be every 40 or 50 kilometers.
Forgive me, this question may be a reference to your Canadian location, but the question is, cold environments can be hard on infrastructure. Do you use any special procedures or precautions to protect your system?
Well, you are absolutely correct. We do have outdoor facilities, systems in a small enclosure that are sitting in a farmer's field surrounded by cattle guards and a light plant in terms of remote power. We certainly don't appreciate those environments because of exactly what you just mentioned. You have significant temperature swings. It's hard to control. And ultimately, you end up troubleshooting more of the system than focusing on the data. Again, that's why we prefer to be in nicer, indoor, secure locations that we can control things like weather and the environment. As it relates to the conduit itself, we do work extensively with Duraline. We have some specialized versions of their product with extra oversheath, more industrial connectors, and the like, so that can better operate from a deployment perspective in harsher environments like Canadian winters, or for that matter, hotter environments in very hot environments as well. So we have taken some precautions at the physical layer for that as well.
Good. I think that just about brings us to the end of the questions. I know usually we also get a question about the replay of the video. Obviously, some people may have not been able to see everything because of having multiple screens up, but Joy should have this posted in the next day or so on both the FOSA website and also a great resource that we have available, which is the YouTube channel, FOSA YouTube channel that has a lot of our old webinars. Additionally, I just wanted to do a bit of a plug for our next webinar that will be on Thursday, like this one, on June 21st. We will be highlighting the work of our technology committee in dealing with rail line applications, and they've done some, the technology committee has done some work in that space, and we'll be doing a presentation on that. So you can sign up for that. You can also look at our past webinars, but thank you very much, Steve, for an extremely informative webinar. I think it's been very helpful for all of us to learn more about high fidelity dynamic sensing. Thank you. And this concludes
it was indeed our pleasure. Thank you very much.
And this concludes our webinar.